All right, so I want to talk about this for a minute. So here's matrix A. And we'll start off with a nice 2 by 2 because we can, I guess. I don't know, why not? So let's do this. Let's just review here. What are the eigenvalues of this fella? And so they would be lambda square minus 10 lambda plus 21 minus 2. Is that right? Yes. Yes. I should have thought this through a little better. One moment while I pause. Sorry, there we go. I put 5s in instead of the 2. How about that? So this is lambda squared minus 10 lambda plus 16. Of course, that's lambda minus 8, lambda minus 2. So 2 and 8 are my eigenvalues. So if a person were to plug those back in, let's say we start off with 2, you're going to get 3 minus 2 is 1. You're going to get 1, 5, and 1, 5. Remember, if you're doing this, you can do it a couple ways. I've showed you this way. That's one way to go about it. Or you can do like your book shows, 1, 5, 0, 1, 5, 0, whatever. And to pull that off, you're going to just, R1 minus R2. Of course, it's always going to look like this when you're finished. So what does that mean? Well, you could do 5x. Well, you 5 times. So in other words, basically what you're saying is this. It's A plus 5b is equal to 0. So then A is equal to negative 5b. So if you let b equal 1, A is negative 5. Okay? So when lambda equals 2, we get negative 5, 1 for an eigenvector. And if you plug in 8, you're going to get negative 5, 5. And you're going to get 7 minus 8 is negative 1. So you're going to get 1, negative 1. So I guess we'll do it your book's way. That's cool with me. So let's go to a little R1 plus 5R2. It's going to give us this. Lovely. So negative 5a is equal, or plus 5b rather, is equal to 0. So a equals b. So 1, 1 comes to mind. Okay. Nice. Now I'm going to do something and you're going to be like, why? What? So just bear with me for a minute and we're going to see what happens here. Okay, now for no apparent reason, this is our matrix A. This is the matrix that is our eigenvalues, or eigenvectors in a matrix. This is the one that went with the 2, I believe, and this is the one that went with the 8, I think you'll find. We're going to call this matrix P, and we're going to call this matrix P inverse. And for no apparent reason, we're going to do just like this. Right now, it's for no apparent reason, but I want to show you something, okay? I typed them into my calculator, and I got that. And you're like, wait a minute, you got this. That's right. What? Jay, there's only stuff on the diagonal. That's right, friend. We call this a diagonalized matrix. And we actually call this matrix D. Okay? And wait, is there a reason why the 2 is on the upper column in the first column? Yeah, because this guy's here. And that's why the 8 is in this column? That's right, brother. Now wait, what if you switched them around? That's a good question. Because I feel like it was completely random why I chose to do it that way. Delete. Let's see if I can do this without doing it wrong. Negative 5, comma 1. So how you doing? Let's get rid of him. I think it's just like this. Negative 5. Oh, fiddle faddle. Oh, because you didn't put an extra to eat there, stupid. There you go. Now what's the problem? For God's sakes. Yeah, I never told you to put a comma there, I don't think, did I? Ah, now what do you want? Oh, because now you got too many of them there. Freaking make up your mind. Criminy. Okay, so I messed something up. Well, bear with me. I messed something up there. I typed something in. Goofy. Oh, I know why. There we go. Because I did it wrong. Okay, if you go back up here, it was 1, -5, and then 1, 1. And then I think I did it in the wrong order in this last one down here. So... oh, it should have been... yes, it should have been -5, 1. And I think I put it in back. Oh, okay, there's your problem. It should have been -5, 1, and... oh, well, hold on a minute. I'm a little confused. I'll do it again. I'll pause you while I do. Never mind, I figured it out. I know what I did wrong. I switched the rows, not the columns. Okay, so I need to switch columns. So therefore, this needs to be written as 1, -5, 1, 1. Okay, because remember, this is still our vector. We've moved that vector over. So let's see if I can do it right this time without screwing it up. So when I plug it in, it's going to be 1, -5. That's the top row. And then 1, 1. There's your bottom row to the -1 times 3, 5. Oh, try again, stupid. So 3, 5, semicolon, 1, 7 times, and then we're going to do this again, 1, -5, semicolon, 1, 1. Done. Yay, it works if you don't screw it up. How about that? Okay, now you're like, well, what did that just show us, Jay? Well, it shows us that it was completely random in the order that which I put it in previously. And so this is kind of interesting. You're like, oh, yeah, I guess it's interesting, but what did you just show, Jay? Well, what I showed is this. If this is D over here, and when you look at that, keep that in mind. Your book starts off naming it kind of weirdly. Your book says that there is a matrix P such that AP is equal to PB. Okay? And it starts off talking about this. Okay? And it says that, and this is the important part here, it says that if A is similar to B, we write this. So when we say that A is, we say similar to B. If this is true, then this is true. Or if this is true, this is true. And remember, when it works both ways, we say it's what? It's an if and only if situation. Okay? And so we say that works out that way. It's kind of I don't know, I guess it's interesting, I guess. You're like, that's kind of cool. How would you solve for B here? Well, it turns out to solve for B, you would multiply by P inverse, which would give you the identity matrix here. And of course, identity matrix times B is just B, of course. Now, what would happen on this side? Well, you'd also have to do this. And so you get P inverse AP would have to equal this. Okay, well, what if I said, interestingly enough, that, okay, well, you did all that. That's great. So then if we specifically call it matrix D, well, this is what's going to happen. And what this is going to do for us every single time, okay, when we make this happen, we're going to get what's called a diagonal matrix. Okay, it's been diagonalized, we say. And on the diagonals will always be our eigenvalues. Okay, and in the same column that they're in will correspond to the column that the eigenvectors went with over here. Okay. Now, we'll get a little more application of this later, but a couple things to think about. Obviously, any matrix A is similar to itself. Duh. If A is similar to B, then and B is similar to C, then A is similar to C. That's transitive property. Nothing fancy about that, right? And I think we all would have figured that. And if A is similar to B, B is similar to A. Okay, commutative. And so that's pretty easy to do. Remember, those all have to be n by n matrices. Now, I think that goes without saying, because when we're pulling off whether something's similar or not, first of all, I've taken inverse. For it to be an inverse, it has to be, well, first of all, invertible. What does that mean? Well, it means that the rows and the columns, rows or columns, if you're going to think about it, have to be what? Independent, linearly independent of one another. Okay, that's number one, which means they have to be full rank. You can say it that way too if you like. And they have to be square, obviously. And so the only way you're going to get P inverse, that has to be square, times A times P. The only way for this to be true is if for them to be n by n's. This is the only way that's going to work. Okay? And so they have to be square matrices to pull that off. Okay? So here's a couple other things here. If A is similar to B, then the determinant of A is equal to the determinant of B. Okay? A and B have the same rank, which, by the way, will be full rank, right? It'll be rank n, by the way. Rank n, by the way. They have the same characteristic polynomial. A and B, same characteristic polynomial. Yep, that's true, interestingly enough. Okay. We'll look at that in a few minutes. By the way, what does that mean? Same eigenvalues. Okay. And A and B have the same eigenvalues. Well, that's what that means. That's what, and it spelled it out for you in the second part of that. Okay. So not terribly difficult there. So and so when we look at this, that's kind of exciting in terms of how to pull this off. So let's just pull one out of our heads and see what happens here. So interestingly enough, I will do one off camera and then I'll come back to you. I guess I forgot to push play there. So for instance, here we have, this is matrix A, this is matrix B, this is P, this is P. And so what we have here, of course, are, PA is equal to PB. I'm sorry, I wrote that backwards. AP is equal to B. AP is equal to PB, okay? That's what we're saying. And so if you look, you multiply it out, sure enough, they're equal, okay? And if you multiply by P inverse to the other side, in other words, you take right here and go 2, -1, 3, 2, inverse, you will get, guaranteed, this guy right here. Okay? But let's look at our A and our B, shall we? Well, let's look at that guy. What would our characteristic polynomial be? I don't know. Let's find out. It would be lambda squared minus 5 lambda. That would be plus 6 minus 12. So lambda squared minus 5 lambda minus 6. Nice. For this one, it'd be 6 minus lambda, 0, 0, -1 minus lambda. So that'd be negative lambda squared. No, it wouldn't be positive lambda squared, you jackass. You can't multiply good, can you? Yep, minus 6 plus 1 is minus 5 lambda minus 6. Done. Yes. Do they have the same determinant? Geez, I don't know. Let's find out. So the determinant here would be 3 times 2, which is 6, minus 12 is -6. What's the determinant here? 6 times 1 is -6, minus 0 is -6. Everything comes into play. Okay? Now, that's kind of the game for that kind of situation right there. So what are we going to do with it? Okay, we're going to come back and do a couple of these, but let's just see what happens here. So, for instance, well, this is number 6 here. It says we have been given this, list the eigenvalues of A and the basis of the corresponding eigenspaces. Okay, so it says this. Recall that you have 2/3, 0, -1/3, 1/3, -1, 1/3, 1/3, goodness, 0, 1/3. So this is obviously P inverse. A is 2, 1, 1. Oops, 2, 1, 1, you jackwagon. 0, 1, 0. And 2, 0, 1. And then P is 1, 0, 1, 0, negative 1, 1, and negative 1, 0, 2. And then, of course, that's equal to 3, 0, 0, 0, 1, 0, 0, 0, 0. Okay, cool. Now, what does that tell us? First of all, it tells me my eigenvalues are 3, 1, and 0. Boom, boom, boom. Now, the next thing it tells us, and it's a little goofy because of the way they phrased it, but our basis for eigenspaces are this. You need this one. You need this one. And you need this one. There they are. Okay? Literally, the basis for the eigenspace is the eigenvectors. That's all they are. Okay? Here's another example, number 10. We'll do number 10 together because that sounds like a fun one. Not really, it's just the problems. Let's just do it and see what's what. 1, 2, 0, 0, 1, 2, 0, 0, 2. Nice, whatever. Okay. It says, is it diagonalizable? And the answer is, I don't know. But you know what I'm going to do first and foremost of all is, I think I'm just going to go see what my eigenvalues are. Ah, yes, there's that. Boom, 1, 1, 2. Okay, remember that's a multiplicity of 2 on that eigenvector value, rather. Let's see what happens here. Boom. So there you have it. You get 1, 0, 0. You've got negative 1, 0, 0. And you've got, that's 1 to 2 to 4, right? 1, 2, 4, 1, 2, 4, 4, 4, 2, 1. Okay. Remember, if you're not sure if that's true or not, look what should happen. Okay. So let's see what happens here. Remember, if we take a 3 by 3, right? And remember, if we evaluate with our particular lambda in place, okay. Excuse me. I'm sorry. Let's actually back the train up just a hair. We'll try something different here real quick for you. So let's start 3 by 3. Remember what happens when we multiply this by our, darn it. What's the last one? 0, 0, 2. What happens when we multiply it by our eigenvectors? Remember that? Okay, so let's do this. I'll pause. You have to watch me type it. Okay, so I've typed it in, you can see, and I multiplied it by, and I chose the last eigenvector. Remember, when you take a matrix A times its eigenvector, and if you do that, well, then you end up with the same eigenvector. That was one of the conditions for the eigenvector. Also, if you plugged in the eigenvalue, so I plugged in 2 everywhere, so it was 1 minus 2 is negative 1, 1 minus 2 is negative 1, 2 minus 2 is 0, times that same eigenvector, and you get the 0 vector. That's literally the definition of how we found the eigenvector to start with, okay? So there you go. There you have it. Yay. Okay? So then the question is it diagonalizable? Okay, cool. Yes, certainly it is, and it looks like this. It looks like this. 1, 2, 0, 0, 1, 2, 0, 0, 2 times 1, 0, 0, negative 1, 0, 0, 4, 2, 1, ta-ta, and then the inverse of that fella. And lo and behold, what should we get? We should get this. Let's see if that's correct, shall we? Okay. And so, let's see. I'm just going to go up here and snag this, get rid of this garbage on the end. And let's go ahead and plug in our matrix. I'm just going to add on our matrix. Don't panic. Oops. I'm just going to go 1, comma, negative 1, comma, 4. And then 0, comma, 0, comma, 2. 0, comma, 0, comma, 1. And then go back to the start. And let's go ahead and insert this guy at the start again. So 1. Darn it, you hippie. Yo, you hip. Oh, for God's sakes. Interestingly enough. Interesting. Well, now that's interesting, folks. That is very interesting. And why is that the case that we're getting that? Don't even have to look, right? Why is that the case? Why is this not possible to write this way? Because P inverse doesn't exist. And why does P inverse not exist? P inverse does not exist because this matrix, this vector here and this vector here are linear combinations of one another. Obviously, if you multiply this one, so this is just row 1 times -1, right? Because that's true, because that means this guy will not have full rank. Therefore, it will not have an inverse because it'll have a determinant that is equal to 0. Okay? And so this one is not diagonalizable. If it were, this is how you would fix it. Okay? So you're going to be asked to do a few of those. Kind of easy to do. Kind of makes it nice. Kind of fun almost. Let's try another one here. This sounds fun. Let's do this one. Ooh, cool. So 1, 1, 0, K. This is our matrix A, and we're supposed to find all the real values of K for which A is diagonalizable. Diagonalizable. Okay? Okay, well, what does that mean? Well, I don't know. Let's find out. So 1 minus lambda, K minus lambda, 1 and 0. This is pretty hot, by the way. So I feel like, okay, you're going to end up with what? It's going to be lambda squared minus K lambda minus lambda plus K equals 0. Okay. Are there some values that won't work, for instance? Okay. Well, I don't know. Let's find out here. So this is really could be written as plus. I'm going to write it like this, I think. Let's do that. How should I do that? Should I go plus lambda and then... No, should I do minus lambda? Minus lambda. And then K plus 1. No, let's put the minus there. There we go. There you go. All right, that worked for you? I think that works for me. And so if you were to use the quadratic formula, it would be the opposite of B. So K plus 1 plus or minus the squirt of K plus 1 squared minus 4 times 1 times 6 is 24 over 2, I believe. And so that's going to be K squared plus 2K plus 1 minus 24 has to be bigger than or equal to bigger than 0. I think. Sound right to you? I think so. Okay. I'm going to pause for a second. It just looks... I knew I was making that too hard. It was just freaking me out, and I don't know why. It's not hard. It's duh. Just think about it, Jay. So the idea here is you're like, okay, well, to pull this off, it says it needs to be for which it's diagonalizable. I'm like, oh, okay, cool. Well, for it to be diagonalizable, right, you need to have separate eigenvalues, right? You can't have repeated eigenvalues, as we saw in the last one, unless that's not always true. You can have separate repeated eigenvalues, but they have to have distinct eigenvectors, okay? Which the last one we saw did not. They were 1, 0, 0, and negative 1, 0, 0. Those not distinct. If one was 1, 0, 0, and one was 1, 0, 1, then that would be fine, okay? But in this case, think about this. When you do this, you're going to be boom, 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 boom. Like, wait, I feel like 1 minus K and K minus lambda. I mean, 1 minus lambda. Yeah, that's what I meant. So you get lambda squared minus K lambda, right? And then plus K equals 0. And you're like, well, how does that do for me, Jay? Well, I'll tell you what it does for me. Don't do that. Do it this way. But what you're saying is that because because there's a 0 here. Because you're saying that this is going to be minus 0, yeah? So it's already in factored format, yeah? So my eigenvalues are 1 and k. Okay? Now, 1 and 1 is going to be a problem. If they're both 1, I feel like there's going to be an issue, right? Think about this. So if you did this 1, 1, 0, 1. If you did this, and you did minus lambda, you're like, all right, let's try this. Well, if I did that, what would you get? Well, if you put in the 1s, you would get 0, 1, 0, 0, I believe. Is that right? Yep. And then if I was, well, and so what would you do here? Well, you can multiply the first guy by anything, for instance, 1, and then 0 on the last one, right? And so that would work. That's fine. There's nothing wrong with that. But you cannot get any different ones than that. So in other words, it couldn't be a repeated repeated vector. It couldn't be multiplicity of, so you couldn't be 1 and 1 is what I'm saying for k. But could k be 2? I don't know. Yeah, sure, I guess. Could k be 3? Sure. 4, 5, 12? Sure, sure. So basically, as long as k is not equal to, k is bigger than 0, k not equal 1, okay, I think we're good to go on this guy. Okay, again, we don't want the repeated root, and it said it wanted to have, it wanted real values of k. All right. Now, could k be a decimal? Sure. Could k be, you know, any fractional value? Sure, it's not a problem. So that's what it would look like. Part A, the first few exercises on this page show that they're not similar matrices. Well, you know what similar matrices have in common, so if you want to show that they're not similar, I feel like just show that they don't have those things in common, and there you go. Okay. Now, in like we're going to do number 36 here together. In general, it's difficult to show that two matrices are similar. However, if two similar matrices are diagonalizable, the task becomes easier. Show that A and B are similar by showing that they are similar to the same diagonal matrix. Then find an invertible matrix P such that yada yada. Okay, so what I'm going to do is I'm not going to do that first, and then in a second I'm going to say this. So if my A is this, so this is 3 and 1, 0, negative 1, and my B is 1, 2, 2, 1. First thing I'm going to do right off the bat is I am going to go and find the eigenvalues here. So the eigenvalues for this guy, 3 minus lambda times negative 1 minus lambda minus 0 equals 0. It's lambda squared. That's going to be minus 3 plus 1 minus 2 lambda minus 3 equals 0. So as you know, that's going to be lambda equal 3 and lambda equal negative 1. So that's going to be 1 minus lambda minus 4 equals 0. Lambda squared minus 2 lambda minus plus 1 minus 4. Hey, look at that. They have the exact same characteristic equation, which means that they factor the same way, which means you get the same eigenvalues. Cool. Same eigenvalues suggest same eigenvectors. Okay, so I'll go ahead and bust them out by hand. Again, just to repeat it, just so that you get the hang of it, I hope. 0, negative 1, 0. Okay. So yeah. So hey, all right, let's do this thing. So what would you do here? Yeah. Okay, so that just feels dirty and weird. Oh, I know why I'm doing it wrong. Duh. One moment, please. Maybe, Jay, if you actually do it right, like, why does that feel stupid? You got to put in an eigenvalue here, you ding-dong. So listen, 3 minus 3 is 0. And negative 1 minus 3 is, I don't know, negative 1 minus 3 is negative 4. That's nice. That's great. Awesome. Wonderful. So in other words, it doesn't matter what you multiply the first one by, and you can multiply the second row by 0. There you go. So that would be this one. And then if you did, remember it was 3 before, so 3 minus a minus 1 is 4. And it was -1, wasn't it? -1 minus a minus 1 is 0. So I feel like that would be saying 4a plus b equals 0. So b is -4a. So if a is 1, b would be -4. And that would be this guy. Is that true? Now here's the thing. I could find it for the other ones. I don't really feel like doing it, though. I feel like just doing this. So what I could say, I could do it a couple of different ways. First of all, I could show this. I could show, where's my p? My p is here. 1, 0, 1, -4. My A matrix is here. 3, 1, 0, -1. 3, 1, 0, -1. And then, of course, this guy, provided that it has an inverse that is a real number. So let's try this. Let's just for fun do it. So we're going to do this a couple different ways. Again, this is mostly, for this part of it that I'm doing right now, is demonstrating that you're just running through and understanding the concepts of what we're doing in terms of the rules. Times parentheses 3, 1. And there you go. Okay, and so then there's a couple ways. You could do that. So this is equal to this guy, which we said was 3, 0, 0, -1. Okay. So that's possible. And then all we'd have to do then is come in and show that those middle ones, this guy here, is similar to our B matrix. So just stick in your B matrix and it'll work for that. And 1, 2. Oh, fiddle faddle. Fiddle faddle. 1, 2, 2, 1. Interesting. Okay, so they have the same eigenvalues. So hold up a minute. Something went screwy there. Let me pause you. And we're back. So if you did 1 minus lambda, I'm just going to go ahead and compute the eigenvalues or vectors for this fella. If you plug in 3, you're going to get -2, 2, 2, -2. And so what does that mean? It means that A is equal to B, so 1, 1. Well, you would have -A plus B equals 0, so A equals B. Or you would plug in 1, -1. So 1 minus minus 1 is 2. 1 minus minus 1 is 2. There you go. So -1. So 1, -1, or -1, 1, whatever turns you on. One of them has to be negative. Okay? This is why this thing here didn't work a second ago. You understand? So we need to make sure that we put that into context. And if I had paid attention to what they were saying to me, I would have caught that. Oh, no, dang it. I would have caught that because it said, show that they are similar to the same diagonalizable matrix. And I didn't read it clearly enough, or I didn't listen to it, I guess is what I'm saying. 1, 1, and 1, -1. Now what? What in the heck did go on here? What's up, yo? Okay, this is ridiculous. Lose that. Oh no, I needed that actually. Sorry, my bad. If you're wondering where the extra brackets come from, that's how you used to have to enter it, and then they changed it where you can use semicolons there. No. Instead of the extra bracket. Now what do you want, you piece of crap? Oh. No. Oh, I know why. Yeah, it doesn't dig that. It wants to do this now because because of the way that it was, and I was editing it, I had to put it in that way without a semicolon. Yes! All right. So, 1, 1, 1, negative 1, to the negative 1 times 1, 2, 2, 1 times 1, negative 1 is equal to 3, 0, 0, negative 1. And since this is true, we say that this is similar to that. And we say that this is similar to that. And so because they're both similar to this, they're similar to one another. And that is for problem number 36. Okay, so that's the game. It's pretty straightforward. Not a very difficult problem to do, I don't think. One moment, please. All right, so that's it. So that's in essence section 4.4. It's not terribly difficult. It really isn't too bad. Now you ask, where do we come up with that? Where are we going to use some of this in the future? In a lot of ways, well, so the similarity bit obviously is why you need to be able to do that to some degree. But also, it's kind of a neat way of just kind of looking at some things, and then it's something that was back in the days of slide rules. It was something we used a ton more. And now I think it's one of those things that I still teach it because, well, number one, it's on the curriculum. I have to teach it, but number two, I think it's helpful to just to be good with our algebra, in our linear, in our matrix algebra, to feel comfortable with some of this stuff, and to feel comfortable with some of the other things that we've done. It's kind of going at it from that standpoint. Okay, I'll do another one here as an example. So it's number 12. I think you'll find 1, 0, 0, 1, 1, 3, 3, 0, 1. This is my A matrix. And I would like to write it in the form P inverse A, P equals a D, okay? Again, to pull this off, first things first, clear, 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 escape, clear, 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 escape, clear. All right, now, I'm going to go to the, try again, Jay, second, 5, 4, 9, cool. Find the eigenvalues of this matrix, so 1, 0, 0. Oops, what are you doing, stupid? 3. Oh, 1, 1, 1. Interesting. So right off the bat, what are you thinking? Oh, I've got a multiplicity of 3 here. Ugh, I don't think I could do this. Yes? Let's find out. Let's don't despair just yet, though, friends. Boom. So, right off the bat, you're going 0, 1, 0. And then you got 0, negative 1, 0. Uh-oh. And then the last one over is 0, 1, 0. Okay, 0, 1, 0. And so what does that say to me? Well, it says these are all not linearly independent, which means that it's not invertible, which means if it's not invertible, I cannot write it in this fashion. Okay, now, bear with me one moment. I'm going to start off with another one here. Matter of fact, I'm going to let you in on a little secret. If you were a teacher and you're like, I would like this. I'd like to do something cool here. Actually, I don't feel like it. Here we go. So I went in and plugged it in. So I got negative 2, 1, negative 2. Okay, there they are. Now I went in and got our eigenvectors. And of course 0, 1, 0. That's an easy one. And then the middle one you can see is 1, negative 1, 2. Pretty easily, I think you can see that. The last one's a little trickier. You're like, exactly. So 0.22, oops, where am I at here? Down, clear. So we're going to do negative 0.6925 13441507 divided by but negative 3.03. Now, I know going in, okay, so it should have been 1 to negative. So it should have been negative 3.03-ish here. This should be 1. And then if you look at it, you're like, well, Jay, I feel like the bottom, this other one should be 0.6968. Four, 3.8, 4.8, 7.8, 7.4, which is basically 3. And that one I'm just going to go ahead and round off to 3. Okay, we know they're not the same, but they're awfully close to the same. Okay, and so then in theory, we should be able to do this. 1, 0, 1, 0. 1, negative 1, 2. 1, negative 3, 3. Okay, and so my point by saying that is that the reason I did this one is I wanted to do one that had repeated roots, but they were different eigenvectors. Are you with me? They are independent eigenvectors. So the last couple we did were, we call that defective eigenvectors actually, and in differential equations, I talk about that a little bit when it comes to solving, because you actually have to solve those. And it's a pretty straightforward process to come about that. And so let's see what happens here. I'll spare you the gory details here. I think I will. I guess I'll pause. Yeah, I'm glad I spared you the carnage. Good night, nurse. I dropped a couple of negative signs. I thought I was losing my marbles. There it is, friends. As you can see, we get what we're supposed to get back out. We get D back out of that mess. Okay, so again, I did that one to show you that in fact, just because you have multiplicity doesn't necessarily mean that this won't work. It only means that if you do not have, well, you have what are called defective eigenvectors. That is, they are linearly dependent on one another. Okay, and so that isn't always true. In this case here, you had lambda equal negative 2 twice, but they were at least two different eigenvectors that were linearly independent of one another. Therefore, you could use them, and therefore your P matrix would have full rank, and therefore you could take the inverse of it, and therefore this could be done. The other ones that couldn't be done because it didn't have full rank. Didn't have full rank because the eigenvectors were the same. Oh, they were multiples of each other. Okay?